Here is an example, something called rising number. A positive integer is called a rising number if its digits from a strictly increasing sequence. So for example, is 1, 2, 3 a rising number? Yes. First digit is smaller than the second digit, and the second digit is smaller than the third digit. Okay? Is 3, 4, 3 a rising number? No, because after 4, this digit is smaller than 4. But rising number requires this digit has to be larger than 4. Is 2, 3, 3, 4 a rising number? No, because 3 is not smaller than 3. 3 is equal to 3. Is 1 a rising number? Yes. So for example, how many 3-digit rising numbers are there? So we consider a set S, that is D1, D2, D3, and each Di can be any number from 1 to 9. And we are requiring D1 smaller than D2 and D2 smaller than D3. The question here is that how big is this set S? So how do we solve this problem? Well, we will count it by what? Enumeration, product rule, and sum rule, or by something called brute force. So suppose we have D1, D2, D3, and now we draw a tree. We draw a tree, then the first case is, for D1, there are how many possibilities? We have 1, 2, 3, 4, 5 up to 9. We have 9 branches, 9 branches, 9 branches, okay? And after that, at this point, we now look at D2. So for D2, how many branches? Can we take 1? No, because we have to make sure D2 is larger than 1. So D2, the smallest one, is 2. And then we can go to 3, 4, 5, 6, up to 8. Okay, you may wonder, can we go to 9? No, because if we go to 9, then there is no more answer for D3. So that means here we stop at 8. Okay, so how many branches are there? Well, there are 7. How many? 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 branches. So for the second digit here, we have 7 branches. And lastly, what about here? Here are all the possible D3, okay, starting from 3 to 9. And then if I start D2 with 3, we can do the same thing. And here are all the possibilities. And after you found all their common patterns, you will find that the total number of cases will be 28 plus 21 plus 15 plus 10 plus 6 plus 3 plus 1 equal to 84. So this is the way you count it. But you can see that if I count using this approach, just for 3 digits, it's very tedious. So is there a way we can do it better? Yes, bijection. So assume we want to count x. And assume we have a bijection from x to y. Okay, recall what is bijection. Bijection is one-to-one injective and onto surjective. So once we have this relationship between x and y, and suppose counting x is hard, then we can count y instead. Because there is a one-to-one relationship between the arrows. That means what? If we feel very difficult to count A, B, C, D, we can count 1, 2, 3, 4 instead. Because there is a one-to-one relationship between A, B, C, D and 1, 2, 3, 4. Because there's no one-to-many mapping, and mapping is unique. That means one element here will point at exactly one element here. There's no overlapping, there's no one-to-many mapping. Every mapping is unique. There's a one-to-one. This is the most important thing, one-to-one. Therefore, if we found that counting A, B, C, D is difficult, we can actually count 1, 2, 3, 4. If counting 1, 2, 3, 4 is easier. So that's the idea. And counting by bijection is a very powerful method. Okay? So actually this is also the reason why the number of R combination of an n set, that means n choose R. How do we count it? We use the binomial coefficients. And why it's working? It's because the number of n choose R and the coefficient in this binomial expansion is a bijection. So that's the reason why we learn the binomial theorem for counting things. Okay, so here's the idea. The idea is, if I have a way to link x and y in a one-to-one onto fashion, then if counting x is hard, I can count y. Okay, so now back to our problem. We want to count rising number. Okay, this slide is showing that counting rising number using the standard approach by sum rule, product rule, and branching using a tree is very, very tedious. So what should we do? The first step when using bijection is we need to have a bijection. We need to find a bijection. What's the bijection? Fact 1 is saying that if I have a rising number, then implies 3 distinct digits. Fact 2 is saying that if I have 3 distinct digits, I can point arrow back to a rising number. In other words, I'm saying that fact 1 means I have an arrow in this way. Fact 2 means I have an arrow in this way. So what is this? This is if and only if, okay? If and only if in the logic. But in combinatorics, we can say that means what? For number of 3-digit rising number and what? The number of way of selecting 3 distinct digits, there's an if and only if. So what is this? Number of 3 rising number. That means this guy, okay? That means this guy. And then we show that from fact 1 and fact 2, we see that they are if and only if with what? This guy and this guy. That means this and this is an if and only if, or bijection in a function sense. So therefore, if we want to count the number of rising digits, we can count the red box instead. So the number of way of selecting 3 distinct digits from 9 symbol is exactly 9 choose 3. So there's 9 choose 3, which is 84. And if you do the analysis using the standard approach, you will get the same answer. Okay, but this is much faster. So here's more examples on rising number. For example, how many 4-digit rising number are there that are greater than 5,000? Okay, greater than 5,000. That means we are only limited to what? 5, 6, 7, 8, 9. we just make sure the first digit is larger than 5, 6, 7, but don't forget we are doing rising number. So if the first digit is 5, 6, or 7, and so on, the remaining digit cannot be 1, 2, 3, 4. So therefore, we have discarded 1, 2, 3, 4 in the very beginning. So that means we can only choose 5, 6, 7, 8 to form our 4-digit number. That means we want D1, D2, D3, D4 from 5, 6, 7, 8. And from this analysis here, number 3-digit rising number is the same as 9 symbol choose 3. So now number 4-digit rising number will be same as what? 5 symbol choose 4. That's this 5. Can we solve it by brute force? We can. So let's list all the 5 4-digit rising number. So we start with 5, 5. We are going to do lexicographical order. That means we will choose the letter following the order. So 5, the next one should be 6, and then 7, and then 8. What's next? We just change the last guy. So 5, 6, 7. What's the next one? Is 9. So we go to 9. Can we move on? 9 cannot go on. So we change the previous one. So we will have 5, 6, 8, 9. Okay. Can we go on? No, because this is the end. So we change the second guy. So 5, 7, 8, 9. Okay. Can we go on? No. So we change the first guy. 6, 7, 8, 9. Can we go on? No. So we change this guy, but that's the end. So 1, 2, 3, 4, 5. These are all the 4-digit rising number larger than 5,000. So how many 4-digit rising number with D4 equal 9 are there? Okay, so that means we have D1, D2, D3, and what? 9. We don't need to write D4. So this is the same as what? This is the same as we want to find a 3-digit rising number with DI equal to 1 to 8. Why there's no 9? Because if I put a 9 here, then this is no longer a rising number. Okay, so it's same as what? Same as how many number here? Choose 3. Okay, so 8 number choose 3. So this is a careless mistake. So be 8 choose 3. So it will be 5 and 3. Okay, so this is wrong. With alphabet A, B, C, D, F, Z up to Z, how many 5-letter rising string with D2 is D, D3 is F are there? So how do we approach? This problem is the same as counting how many rising string as question mark, DF, question mark. So we want rising number, right? So for this guy, it can be anything before D. So A, B, C, right? So there are 3 choices. Okay, this is correspond to here. What about this? This can be anything after F. So it can be G, H, I, so on until Z. Okay, so there are 20 letters from them. So it's 20 select 2. Okay, so the number of ways to choose for these boxes and the number of ways to choose for these 2 boxes is independent. So we do a what? A Cartesian product. So the number will be a product rule. It will be this 3 times this 20 choose 2. Okay, which give me this.